Have you ever wondered if there's a shortcut through space that could take you from Earth to the other side of the galaxy in just seconds? What if I told you that scientists have actually theorized about cosmic tunnels that could make this possible? These aren't just science fiction fantasies. They're called wormholes. And today we're going to dive deep into one of the most mind-bending concepts in modern physics. Picture this. You're holding a piece of paper and you want to get from one corner to the opposite corner. You could trace along the edge, taking the long way around, or you could fold the paper and poke a hole straight through, creating a direct path. That's essentially what a wormhole represents in the fabric of space and time, a theoretical shortcut through the universe itself. But before we get ahead of ourselves, let's start with the basics. What exactly is a wormhole? In the simplest terms, a wormhole is a hypothetical tunnel-like connection between two separate points in spacetime. Think of spacetime as a vast, flexible sheet that can be bent, twisted, and potentially punctured. A wormhole would be like a tube connecting two distant regions of this cosmic fabric, allowing matter, energy, or even information to travel between them almost instantaneously. The scientific name for these cosmic shortcuts is actually Einstein-Rosen bridges, named after Albert Einstein and Nathan Rosen, who first described them mathematically in 1935, but the term wormhole was coined much later by physicist John Wheeler in 1957, and honestly, it's much catchier and easier to visualize. Now you might be thinking, this sounds like something straight out of Star Trek or Star Wars. And you're not wrong. Wormholes have been a staple of science fiction for decades. But here's what makes them fascinating. They're not just wild imagination. They actually emerge naturally from Einstein's theory of general relativity, which is our best current understanding of how gravity and spacetime work. Einstein's equations suggest that spacetime isn't just empty void. It's a dynamic, malleable thing that can be curved by mass and energy. Massive objects like stars and planets create dips and curves in this fabric, and we experience these curves as gravity. But the equations also allow for more exotic possibilities, including bridges or tunnels connecting different regions of spacetime. Let me paint you a clearer picture of how this would work. Imagine you're an ant walking on the surface of an apple. If you want to get from the top of the apple to the bottom, you'd normally have to crawl all the way around the curved surface. But what if someone drilled a tunnel straight through the core of the apple? You could enter the tunnel at the top and emerge at the bottom, having traveled a much shorter distance through the apple's interior rather than along its surface. In our universe, the surface is our normal three-dimensional space, and the interior would be a higher dimensional realm that we can't directly perceive. A wormhole would be like that tunnel through the apple's core, a passage through this higher dimensional space that connects distant points in our regular universe. But here's where things get really interesting and complex. While Einstein's equations allow for wormholes to exist mathematically, they also reveal some serious problems with the idea. The biggest issue is stability. According to our current understanding, any wormhole that forms naturally would be incredibly unstable and would collapse almost instantly. We're talking about time frames so short that even light wouldn't have time to travel through. Think of it like trying to keep a soap bubble tunnel connecting two rooms. The moment you create it, surface tension and other forces would cause it to pinch shut and disappear. Similarly, the gravitational forces around a wormhole would tend to squeeze it closed before anything could pass through. This brings us to one of the most crucial concepts in wormhole physics: exotic matter. For a wormhole to remain open and stable, it would need to be supported by something called exotic matter or negative energy density. This isn't the same as antimatter, which we know exists. Exotic matter would need to have properties that violate what we call the energy conditions. Basically, it would need to have negative mass or negative energy density. Now you might wonder, does exotic matter actually exist? The honest answer is that we don't know for certain. Some quantum effects, like the Casimir effect, do produce regions of negative energy density on extremely small scales. The Casimir effect occurs when you place two metal plates very close together in a vacuum. The quantum fluctuations of empty space actually create a region between the plates with less energy than the surrounding vacuum, effectively creating negative energy density. However, these effects are incredibly tiny and localized. To keep a traversable wormhole open, you'd need enormous amounts of exotic matter distributed throughout the wormhole's structure. We're talking about quantities that might be impossible to obtain or manipulate with any conceivable technology. Let's explore what traveling through a wormhole might actually be like, assuming we could solve the stability problem. Contrary to popular depictions in movies, the journey wouldn't necessarily be instantaneous. You'd still need to travel from the entrance of the wormhole to the exit, but the distance through the wormhole could be much shorter than the distance through normal space. Imagine two cities that are 1,000 miles apart on the surface of the Earth, but connected by a tunnel that's only 10 miles long. You'd still need to travel those 10 miles through the tunnel, but it would be much faster than driving the 1,000 miles on the surface. Similarly, a wormhole might connect 2 points that are thousands of light years apart in normal space through a tunnel that's only a few light hours long. The experience of traveling through a wormhole would likely be unlike anything we can easily imagine. The gravitational fields around the wormhole entrance and exit would be extremely strong, potentially causing significant tidal effects. These are the same forces that cause ocean tides on Earth, but much more intense. Depending on the size and properties of the wormhole, these forces could range from mildly uncomfortable to absolutely lethal for any traveler. There's also the question of what you'd see during the journey. Some theoretical models suggest that the interior of a wormhole might be filled with exotic radiation, or might provide glimpses of the higher dimensional space through which the tunnel passes. Others propose that the journey might appear completely ordinary, like traveling through a normal tunnel, just with very strange gravitational effects. Now let's address the elephant in the room: time travel. Some types of wormholes, particularly those called traversable Lorentzian wormholes, could potentially allow for time travel under certain conditions. If one end of a wormhole were accelerated to high speeds or placed in a strong gravitational field, time dilation effects could cause time to pass differently at each end. This could create a situation where entering the wormhole at one end and exiting at the other could bring you back to an earlier time. However, this possibility brings up all sorts of paradoxes and logical problems that physicists are still trying to understand. The grandfather paradox, where you could theoretically go back in time and prevent your own birth, is just one example of the logical nightmares that time travel-capable wormholes could create. Some physicists have proposed that the laws of physics might have built-in protections against such paradoxes. Stephen Hawking suggested something called the chronology protection conjecture, which proposes that the laws of physics somehow prevent the formation of closed time-like curves, paths through space-time that loop back to their own past. Beyond the theoretical physics, there's also the practical question of whether we could ever detect or create wormholes. Currently, we have no direct evidence that wormholes exist anywhere in our universe. If they did exist naturally, they might be microscopic, existing at the quantum scale, where the smooth fabric of space-time begins to break down into a foam-like structure of tiny wormholes constantly appearing and disappearing. Some scientists have speculated about whether microscopic wormholes might be created in high-energy particle collisions, such as those that occur in particle accelerators, like the Large Hadron Collider. However, even if such tiny wormholes were created, they would likely evaporate almost instantly due to Hawking radiation, the same process that causes black holes to slowly evaporate over time. The search for larger, naturally occurring wormholes involves looking for their gravitational signatures. A wormhole would bend space-time around it in distinctive ways, potentially creating observable effects on the motion of nearby stars or the path of light passing through the region. Some researchers have even suggested that certain astronomical observations, like the behavior of stars near the center of our galaxy, might be better explained by the presence of a wormhole rather than a supermassive black hole. However, these alternative explanations are still highly speculative, and the conventional black hole explanation fits the observations quite well. The scientific community remains appropriately skeptical about claims of wormhole detection until more concrete evidence can be provided. There's also the fascinating possibility that what we call dark matter, the mysterious substance that seems to make up about 27% of our universe, but doesn't interact with light, might be related to wormholes in some way. Some theoretical models propose that dark matter might actually be ordinary matter located on the other side of microscopic wormholes, making it effectively invisible to us while still exerting gravitational influence. When we talk about the potential applications of wormholes, assuming they could be made stable and traversable, the possibilities are staggering. Interstellar travel, which currently seems impossible due to the vast distances involved, could become routine. A journey to the nearest star system, which would take thousands of years with conventional propulsion, might be reduced to days or hours through a wormhole. But the applications wouldn't stop at transportation. Wormholes could revolutionize communication, allowing instant contact between distant parts of the galaxy. They might enable new forms of energy generation or provide access to resources in remote regions of space. Some speculative proposals even suggest that advanced civilizations might use networks of wormholes as cosmic infrastructure, creating shortcuts throughout their galactic territories. Of course, these applications are all highly speculative and depend on overcoming enormous theoretical and practical challenges. The energy requirements alone for creating and maintaining a traversable wormhole would likely be astronomical, possibly requiring the total energy output of entire stars. The study of wormholes also connects to broader questions about the nature of our universe. Some theories in cosmology propose that our universe might be connected to other universes through wormhole-like structures. These could be naturally occurring features that formed during the earliest moments after the Big Bang, when the fabric of space-time was still extremely malleable. In the realm of quantum mechanics, there's a fascinating concept called quantum entanglement, where particles become connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Some physicists have proposed that this spooky action at a distance might actually be mediated by microscopic wormholes, connecting the entangled particles. While this idea is still highly speculative, it represents an intriguing connection between wormhole physics and quantum mechanics. Recent advances in our understanding of black holes have also shed new light on wormhole physics. The discovery that black holes have temperature and entropy, and that they gradually evaporate through Hawking radiation, has led to new insights about the relationship between gravity, thermodynamics, and information theory. Some of these insights might eventually help us understand whether stable wormholes are truly possible, or if there are fundamental reasons why they can't exist. The mathematical tools used to study wormholes have also found applications in other areas of physics. The techniques developed to analyze the stability of wormhole spacetimes have been useful in studying other exotic objects like cosmic strings and domain walls. These connections highlight how theoretical research in seemingly esoteric areas can have unexpected benefits for our broader understanding of the universe. As we continue to push the boundaries of physics and astronomy, new discoveries might shed light on the possibility of wormholes. Advanced gravitational wave detectors might be able to detect the distinctive signatures of wormhole collisions or formations. Future space telescopes with unprecedented resolution might spot the gravitational lensing effects of wormholes if they exist in our galaxy. The development of quantum computers and more powerful mathematical techniques might also help us better understand the complex equations that govern wormhole physics. Sometimes, theoretical breakthroughs come not from new experimental data, but from finding new ways to solve old equations or from recognizing previously overlooked connections between different areas of physics. In conclusion, wormholes remain one of the most captivating concepts in modern theoretical physics. They represent a perfect example of how rigorous mathematical analysis of well-established physical theories can lead to predictions that seem to belong more in science fiction than in scientific journals. While Einstein's equations permit the existence of these cosmic shortcuts, the practical challenges of creating or finding stable wormholes are enormous. The exotic matter required to keep them open might not exist in sufficient quantities, or might be fundamentally impossible to produce or manipulate. The energy requirements could be beyond the capabilities of any conceivable civilization. The stability problems might be insurmountable, causing any wormhole to collapse before it could be used. Yet the possibility remains tantalizing. If wormholes do exist, or if we could somehow learn to create them, they would revolutionize our understanding of space, time, and our place in the cosmos. They could transform humanity from a species confined to a single world into true citizens of the galaxy, connected to distant realms by tunnels through the very fabric of reality itself. Whether wormholes will remain forever in the realm of theoretical physics and science fiction, or whether future discoveries will reveal them to be real features of our universe, they continue to inspire scientists, writers, and dreamers alike. They remind us that the universe is far stranger and more wonderful than our everyday experience suggests, and that the boundaries between the possible and the impossible are not always as clear as they might seem. The journey to understand wormholes is far from over, and each new discovery in physics brings us closer to answering the fundamental question: are these cosmic shortcuts real, or are they simply beautiful mathematical constructs that exist only in the realm of theory? Only time and continued scientific investigation will tell.